I wanted to go through an example of a crystal structure refinement of a pyroxene because it's a good example of a basic type of disorder being a split occupancy. Pyroxenes also have a lot of chemical substitution within the same crystallographic site, so it makes for a really good example. So what I'm going to do is open up, so I have the file open already here. Actually, I'll show you just some examples of what the structure, a typical pyroxene structure looks like. It's one of the first complex crystal structures solved by Lawrence Bragg. The structure that he solved was essentially a N-member magnesium structure. This one has some iron substitution. So you see this octahedral site here in the middle. That has probably 15% iron I've modeled in this. And you'll also see this weird thing going on with the blue calcium. The site, this what we call M2, is split between two slightly different positions because, you know, some small percentage of the time the site is actually occupied by magnesium, which tends to have shorter bond lengths than calcium or sodium that can also occupy the site. So I'll show modeling that type of disorder and just basic chemical substitution, which isn't really disorder, but the split occupancy is. Also, this has a split occupancy of an oxygen, and the tetrahedral site is basically just silicon. This is a silicate mineral, but aluminum can substitute in there too. I'll show you how to refine that and how to just tell it what the chemical abundances are, because for this sample I actually have chemical data. So normally with an electron microprobe or however you analyze them, you may be reporting them in weight percent oxide, like I've just shown with calcium here. Convert it to atoms per formula unit for minerals, which is pretty easy with silicates, and normalize to a 6 oxygen basis. These are the ratio of the chemical constituents of the mineral. And the beauty of the crystal structure solution is you don't necessarily need to know that we're normalizing to 6 oxygen. We can actually figure that out with X-ray crystallography. In fact, all we really need to know is some of the major elements in it. We couldn't really resolve between titanium and chromium in the structure, but we can actually refine some of these other things to match what we analyzed chemically. But knowing the structure gives you the basis if you're doing this type of mineralogical study. And yeah, so there's different crystallographic sites. So calcium and sodium, very similar in size. They belong to the M2 site that we call it in this structure. It's kind of a weird 7 coordination with oxygen. M1, your typical octahedral site with iron magnesium dominating, but maybe some other lower abundance stuff in there. Tetrahedral site is pretty typically dominantly silicon and a little bit of aluminum and sometimes very small amounts of tetrahedral titanium. And of course that 6 oxygen basis. So I'll show how to actually plug in these directly into ShellX, basically forcing it to use these ratios using some sort of intuition, but with the structure we basically know where things go in what ratios. So I'll show you that and also how to just refine them. So if we didn't know what the ratios of iron and magnesium in the octahedral site was, you can just refine that also. So first thing I should probably do is enter in this information. Augite is typical pyroxene composition. CaANAFeMg, Ti, chromium, aluminum, silicon, oxygen. I think that's... yeah, that's all we really need. You can enter in the exact ratios if you want here, but it's not really going to make a difference. And I'm not going to enter anything else in here for now. And the first step is to harvest the reflections that you collected. So I already copied and pasted all the reflections into this folder. The collection strategy here was a little bit different. It was just using someone's preset formula. So there's a ton of frames per run. And actually, I think I'm going to just harvest all of them and fast forward through that part to show you the end result to see what a full reciprocal lattice looks like. So it looks like there's 7 runs. And someone is missing their detector correction. And I'm going to use a pretty high threshold though, 30. So generally you use 20 I over sigma I. 7 runs, and there were 900. You do not have to do this. You only need like 30 images per run for however many runs there are to get a basic unit cell. But I want to show what a full collection looks like, and if there's twinning or something, we can look for that a little bit easier if there's more reflections. And I'm going to store that in the gray group as the default. But this is going to take a while, so I'm going to fast forward through this. Alright, now that I've harvested a ton of reflections, again, way more than necessary, there's over 3,000 in the gray group. I'm going to look at the frames actually really quick on a scale of 1 to 1,000 counts. And you'll notice that the spots, our reflections, are quite intense, which is okay. If we look at the most intense one, I'm just going to check to see if it's overexposed. And it's not. So even though it's very intense, the top of the peak is not actually flat. If it was flat, it would indicate that it exceeded the dynamic range of the detector itself, and that wouldn't be the best. That would be an overexposed reflection. And the reason that occurred with this sample is because I picked a large crystal. It wasn't really meant for X-ray diffraction in the first place. And someone analyzed it on a very modern setup, very new detector and new X-ray tube. So even at the minimum exposure time of, I don't know what it is, a second or a half a second, these reflections are still extremely intense, which is okay. It could indicate that you can have absorption problems, but really I don't think it's going to be an issue with the sample. And in fact, it actually really improves our resolution in the long run because our reflections represent our Fourier components of the electron density map. So if we can detect higher angle reflections, those contribute to finer periodicities in the electron density map. Low angle reflections give the general idea of the structure, so they're very important for that. But high angle reflections make it possible to resolve detail, basically. Anyway, so I'm going to index this unit cell. No need to do anything with this right now, I don't think. And it should come up with something that is crazy. So the first first one looks like some kind of supercell. I don't know why it came up with that, but the second one gives us a good cell to start with. I'll refine it once, and we have plenty of data to refine to, which gives us those very small plus or minus values. Bravai lattice is in fact 985 monoclinic C, which is correct for a pyroxene. That is the exact lattice that it should have. If that's not the case, you might have to do some manipulating later on, or try to figure out in a reciprocal lattice viewer. And we're going to look at it anyways because I wanted to show you what a full collection actually looks like after I'm done refining this a few times. Because again, we have so many reflections, that'll actually give us a really good starting point. And it's not really necessary, but it does help the integration a little bit, because the integration is presuming that your lattice is correct so that it can fit a box around the intensity maxima and optimize the unit cell at the same time. So it's a way of approaching crystal structure and the data reduction if you're concerned about twinning. So I'm going to view it. And of course, after refining a few times, it looks very nice. And I don't see any indications of twinning necessarily. There are some weird reflections that I see, because you can imagine if I wanted to describe the repetition of a reflection, it would be from here to here or from here to here, and that would just repeat over and over again. That's a lattice that you can visualize in this axis. There are many lattices that you can fit, but I think it's pretty clear how reciprocal lattices work, and what is diverging from this lattice are some of these reflections that occur between what appears to be the dominant domain. And we can use our incommensurate mode just like with modulated structures. This is just a way of transforming the data to see everything that doesn't correspond to the main lattice. So everything that corresponds to the main lattice here that we just selected should be in the middle. In fact, I'll just highlight those and I'll assign them to a different group. This is just a shortcut for separating out lattices. It doesn't mean that the structure is actually an incommensurate modulated structure. And now you see that in like 3 seconds I just separated out those. Now this doesn't really mean anything for the integration, because the integration is already going to use this lattice anyway, and it'll probably just ignore those other reflections, and those reflections may be some inclusion in the crystal that I didn't know about, or maybe it has to do with a bit of disorder that occurs throughout. But yeah, there's some interesting nuances in this, but looks like a good collection overall. And if we wanted to just ignore those gray reflections, we can refine our lattice further with only the green group if we wanted to. Say if I go refine and go here and now select the green group, this would actually improve our initial unit cell slightly, not much. But anyway, we have a unit cell that we can now integrate And before I do that, since I have a cell, I will index the crystal faces to get a good, some good dimensions on this crystal. And as you can see, the crystal is gigantic. I mounted this crystal a long time ago, and as I said, it was never really meant for this X-raying, but we ended up X-raying it anyway. So I'm going to bring that plane in, one of these planes into the view of the screen here. It's a very platey shape here. And of course, I've shown how to do this in other videos before. Yup, way too big of a crystal. Was never meant for X-raying because it is over 1,000 microns across. Yeah, generally, even on my old setup of a X-ray diffractometer, you only need anything less than 300 microns, between 100 and 300. But that's all right. And now I think it's time to integrate. And yes, so you see that our estimated resolution limit is very low. And the reason for this is because we're detecting high angle reflections again. So if we take our Fourier transform of our diffraction pattern, or in our diffraction pattern, the high angle reflections correspond to the fine periodicities of the image that is our electron density map. All I need to do is find the runs, which it does automatically, choose, and start integration with this unit cell. And so far it's looking really good with our spot shapes. And they're a little bit oblong in the vertical orientation because of the spot shapes are essentially the reciprocals of the crystal dimensions. That's one of the contributors to the reflection shape. Other things can be things like unit cell twinning and mosaicity, which is the dispersion of the unit cell parameters of the macroscopic crystal. But that is one thing. So yeah, we'll see how this goes. All right, didn't take too long because there was only 7 runs, even though there were a lot of frames per run. And if you scroll through, you can find a few bits of information. The orientation matrix, which is denoting the orientation and dimensions of the unit cell, but in reciprocal space, so that can be converted if you want the actual orientation as mounted on the goniometer. There's a lot of other things being refined throughout this, but one of them is the fitting the box between the individual reflections in the frames, and that's what these are. So you could see that the intensity maxima for whatever reflection this is centered here, and very high counts. So yeah, each thing gets its own little matrix. But now that we've done that, we can scale the data. And yeah, that's the Lowy group, so I already know what this sample is. You know, if you don't know what the crystal structure is, you may have to go through a little bit of trial and error. But this is a basic example. I don't have to do anything special with the scaling. this because it's not twinned, nor is it a modulated structure. And I will call it a medium absorber and just refine this. And it converges on 3.5-ish. I believe that is a measure of the internal consistency of the Laue group, so of symmetrically equivalent reflections. You always have Friedel opposites, which should be very similar in intensity, but having an R of 3.5% is quite good, so we'll keep going. And now, it's been a while since I've done a refinement, but now we go to XPrep for the space group symmetry. Very easy. And there are 0 lattice exceptions to either primitive or C-centered lattices, and of course it always picks the highest symmetry, so it should be C. So I'll press enter. A985, which is good. I'm okay with that. Of course, if it said that to use the B, since it rearranges the axes, I wouldn't want to do that because minerals, you always want to use the standard setting. And in this case, it's easy because this is the standard setting. So press enter. But that's an option for you. Now we will determine the space group now that we know that it's C monoclinic, and use the combined field of merit to determine that, you know, anything near 1 for this value, or anything that's nearest to 1, would be your space group using the world of statistics. So it's C2 over C, which is in fact the case for pyroxenes, for monoclinic pyroxenes at least. And this will list some of the cutoffs in resolution, anything, give you an estimate of your highest possible resolution in your electron density map, depending on, again, the detectability of high angle reflections. Enter, enter. We already entered a formula, so we don't have to enter it here, even though the formula is not right. As long as you list the constituents, that'll help you at this stage. Because we can refine those ratios or use the ones from our chemical data. And we'll just use the default settings from here on, because we're not dealing with a twin structure, modulated structure, as I said. So we're done with determining the space group of being C2 over C. So now we'll go to solve structure, and at this point, you could also just transfer the files to whatever shellx. You know, you can use the command prompt if you wanted to run shellx from this stage, referencing the ins file and the HKL file. But we'll stick to Apex 3 and get an initial solution, which is our first round of numerical analysis, which comes up with a C2 over C lattice and R1 of 12.5%, which is not that good, but definitely an okay starting point, I think. And I didn't mean to do that. I want to go to refine and copy res to ins. And it's telling me this information, which I will just refine to start off with. So yeah, 10%. I've got to imagine this structure is not going to turn out that well, but usually this first R R1 gives you an indication of how things are going to go. Because, I've done pyroxenes where the starting point is like 5%, and you can get it down to like 1.5%. But this one may not go quite as well, but that's all right. As long as we give a decent model for what our data is, it could have to do with the dimensions of the crystal and quality of the crystal. I could have done a little bit better with, but that's fine. So let's start with our refinement. All right, so at this stage, I will demonstrate the version of refinement where you just refine the dominant constituents and the ratios of the elements. For example, this pyroxene is a calcium, magnesium, iron dominant. Of course, silicon in the tetrahedral site, and those 3 oxygens. These are all correct in their positions and roughly in their occupancy, but the fine details aren't necessarily correct, because there's probably, this site isn't all magnesium. It's probably 10% of the time or something like that it's going to be iron, and we actually know that from our chemical data that some percentage of the time the same site is not magnesium. So we have to fit all of this stuff into the structure. And the first round of refinement that I'm going to demonstrate here is just going to assume calcium, iron, magnesium, silicon, and then oxygen, and that's it. Which will give us a really good R value, or at least the optimal R value, because we're going to be refining all those ratios. If we actually plugged in the exact formulas, it might not be quite as good, because we're not actually refining as many parameters. So even though it's better numerically, it won't give us a better R value per se. So first of all, I'm going to organize this a little bit. Actually, I should just show it in the listing first. Let's see here. There's going to be some warnings about some stuff, including the fact that the formula is not going to match because I didn't enter in the exact ratios, but that shouldn't be a problem. What I want to look at right now is to make sure that it's attempting to assign the correct sites to the correct element. So if calcium has a bond length of 2.3 angstroms in a pyroxene or any mineral, pretty much, I would definitely believe it, because that is a very typical bond length. And same with silicon being 1.6 angstroms. That is very believable. Magnesium and iron typically do have these bond lengths of around 2 to 2.2 angstroms. So those assignments seem to be correct. And in fact, that is how they are assigned in ShellX, in part, I think. Well, it might be just scattering factor. I should correct myself on that. So if it doesn't assign them correctly, it's because it's assigning based on scattering factor. So just to organize, I typically like to have it, Command Z. I typically like to have it in this order. And another thing that you should probably do if it's a known mineral or known material is put it in convention, which I showed in a different video. That would be going to like crystal structure database, of course. Entering in some version of the mineral. even though this is augite, I will enter in diopside and use those coordinates so that you're consistent with other authors' refinements of the structure. If it's a new one, I don't think it's as necessary for obvious reasons. But you would normally want to do that, but I just don't feel like doing that, and it doesn't matter that much for this because I'm not going to publish this. So I'm just going to leave it out of convention. But you can see that calcium 0.5 some number and 0.75 may not be the same as 0 some number and a quarter. So it's like kind of the reciprocal in a way, or occurring at some other increment. But the actual position is the same. It may just be a shifted origin or something like that. So this is calcium in the M2 site. So I'm going to label it CM2 is probably a better way of doing it, just to copy some of my colleagues' way of doing it. Magnesium in M1, so MM1 is a fair way of saying that. And of course this number here just corresponds to the number listed on the structure factor, or scattering factor, not structure factor. So AL would be 1, CA is 2, MG is 5, and that's how that all works. And there's only one tetrahedral site, so I'll just erase that and just say 1. One, 2, 3, and just to give it something to refine, I'll put an extinction correction, which this has to do with the absorption issues that the sample has, because the sample's pretty large. And that'll fix it a little bit. So you see that dropped down the R value by 2.5%. And I will copy res to ins. I should also adjust the weight. Copy res to ins. Okay. So here's a starting point. We haven't done a whole lot at this stage yet, and typically at this stage, rather than splitting occupancies and dealing with disorder right now, since I think this is a good starting point, I'm going to go anisotropic. So because of the temperature of the room, or whatever temperature this was collected at, there's going to be a certain displacement of the atoms associated with it. And this anisotropic command is used pretty much universally. So I will refine that now. But you don't want to refine it too early. Not until you try to get the basic structure down first. So already we're down to an R1 of 4%-ish. Again, this isn't going to be the best refinement in the world, but we will deal with it. I'm just going to change the weight a little bit. Won't really do much. And now I'm going to start splitting occupancies, because the major difference right now, I would say, is the fact that some iron is occupying the magnesium site, most likely. First of all, based on the chemical analysis. 2, this is a natural occurrence of a mineral, and that always happens. Iron and magnesium always substitute for each other in most settings geologically. And 3, I'm sure there's some way of checking those differences in the electron density. So that would be this position, which appears as a box because it's not well modeled on the E80P. The atomic displacement is non-positive definite, which could be because of the fact that it's split between different atoms in part. So I'm going to just split that site between two. I mean, it's not splitting the site, it's just chemical substitution. I should make the distinction there. So I'm going to copy, and I'm just going to duplicate the M1 site. But the next one is going to be iron, so I'm going to say FM1, and I'm going to change the number so that it actually tells it that it's iron, which is 1, 2, 3, 4. Okay. But the other thing is we have to change this site occupancy factor to a different free variable, or at least, yeah, that number, so that it corresponds to something that we can refine, which will be this 0.6. So I'm going to change that to free variable 2. I should clarify this really quick. This 0.5, the 0.5 is the site occupancy factor, and the number 1 is the free variable that it corresponds to. So this first number needs to be 2, because this free variable is the scale factor, or one of the scale factors used. And this has to be -2, actually, because otherwise I would be saying that these have the abundance of that are the same, which is not true. It has to be split between, it has to be some ratio within the same site, which is indicated by a minus sign. This is one of several ways of doing this. But we want to indicate that we are splitting the same position between two elements, which are magnesium and iron. And we're giving it a starting point of 0.6, and that value will be refined when we click refine. But before we do that, we have to put a constraint. We have to put two constraints. One saying, this EXYZ, saying that those two elements occupy the same space, because otherwise what it would do is refine the fractional coordinates of the atom's position. Right now they're the same, but if we click refine, it would probably change. So we want to tell it, don't change the position of MM1 and FM1. That is the syntax of that. Nor do we want it to change its atomic displacement parameters. So we will put E80P, atomic displacement parameter, for those same two elements. And we will now refine it. And it looks like I didn't forget anything. So we have modeled that, and we've dropped the R1 to 3.6. And essentially what this is telling me is my estimate from earlier was kind of correct. 10% iron, 90% magnesium in that site, more or less, just based on the contributions to electron density. What else can we do here? Well, we can scroll down and look at our Q peaks. These indicate electron density in the sample, or in the unit cell. And you'll notice that there is one anomaly here at the top being kind of high. I think this is indicating 2.8 electrons per cubic angstrom is what that unit is saying, even though it depends on the refinement. But that is definitely enough to be concerned about, and something that we should look at. We can do it purely on the computer, but it's nice to see it graphically. And you'll notice that that Q1 is right next to the calcium site. Very close. And that's also obvious by the numbers. 0.5, 0.22, and 0.75 is very close to 0.5, 0.29, 0.75. And that is our split occupancy. And it's probably not calcium. It's some element like magnesium or iron that is occupying that site. But because its bond lengths are slightly different, the actual atomic position is slightly different. So rather than using the EXYZ command, it actually does have a different atomic position. And we can retain the atomic displacement parameter of the other thing in the site. But we also have to use this ratio between, sometimes it's the calcium site, and then some small percentage of the time it's this alternate atom occupying that site, that slightly different position, but the same site, we'll call it. So what you do here is I'll just copy and paste this, duplicate it, and I'm going to start with saying it's magnesium, just because there's more magnesium in the sample. And normally the way that naming goes with split occupancies of this type is you call it prime. So this is MM2 prime. So the alternate atom in that position, and we have to assign it a different free variable, 0.6. This will be 3, and the other will be -3 to indicate the ratio of them summing to 1. And so I have our starting point of 0.6, but also we need an EADP on that between, I forgot, I duplicated this site, but you want to use the coordinates of from the Q peak, of course. So that would indicate the position of the split site. And now I will copy down the EADP of CM2, and MM2 prime. 0.63. I think that's good. So I will click refine, copy res to ins, and we've dropped down our R to 2.06 now, which is a lot better than I thought we'd get with this sample already. Also, I should probably adjust the weight. So I will refine that. Which of course doesn't really do much. And maybe I'll do it one more time. You can also just change the number of iterations. This is 10 least squares iterations used in ShellX. And 2.07. Sounds good. And this is almost done. This is probably the best that we're going to get with our R1 for this sample. Other pyroxenes you get in the 1.4, 1.5% range. Very good crystal structure to refine, typically. Also, I should mention, it looks like if it indeed is magnesium dominant, it appears that 80% of the time calcium is occupying M2, and the other 20% of the time it is the magnesium in the alternate position. And we can look at that. Looks kind of like our model from earlier that I showed in Vesta, where you have those split occupancies. But at this point I haven't done the final refinement. This would definitely be acceptable at this point, though I'm just refining the dominant chemical constituents. So what should we do now? Looking at Q1, let's take a look at that just to check if the oxygen position is split in this pyroxene, or at least if it is detectable, because normally if the free variable refinement of anything that is split is less than 5%, you don't really model it because it's outside the ability of X-ray diffraction, even though I kind of just go with whatever. Q1 is this weird, it's halfway between the tetrahedral site and the oxygen. So this is silicon and this is one of the bonded oxygens. And this is talked about in literature about pyroxenes. Actually, they think it's a sigma bond or a pi bond of some kind that's leading to some extra electron density. That's what I've read about it, but it's like always there. It could also just be an artifact of the Fourier synthesis, but that's what people have said, so we can't really do that much about it. So that means that we're at a good point. We're detecting things that are either artifacts or very minor nuances that people have discussed in the literature. And I don't really see any oxygen that could be modeled effectively, because if Q1 is that one, everything else doesn't really stand out of the electron density of everything else. So I think we're at the end of the rope with this sample in terms of just refining it with these elements. The next step could be entering in the composition. So if you know the composition of the structure that you're refining, as we do here, like we know that it's 0.71 APFU calcium, that's not too different from what our refinement tells us of being 0.79. That is pretty nice. But what we can also do is just force it to be that value and exclude these. So to do that, we're just going to go back to everything's going to be ones. We're going to get rid of that. We're going to get rid of our... Well, I shouldn't have done that, actually. I'm going to leave that one. And E80P, maybe I should leave. Yeah, you want to actually leave these positions. But what we're going to do is assign a fraction for the site occupancy factors. The reason that these are 0.5 is because they're on like a mirror plane or something, or a two-fold, I guess would be the equivalent. A four-fold, this would be 0.25 if the atom is lying on a four-fold axis. Things like that. It just indicates the fraction of electron density is being repeated either like by symmetry. So if you're going to actually assign a fraction to the calcium site, I think the strategy here, these situations get a little bit complex, but since all calcium is going in this site, and we're pretty sure of that because of the size of calcium can only be accommodated by this site in this crystal structure, we can say 0.7 times 0.5 equals the site occupancy, the new site occupancy factor. So if I bring up a calculator, let's try that. 0.71 times 0.5 equals 0.355. So we can just tell it that since we know it from other data, it's actually 0.355, for example. And you'd go through that with everything, including silica, which we would actually split. So we'd go split that, same position, except we want it to, the other position to be aluminum, because we know that silicon and aluminum coordinate in the same site, and I don't know why it just did that. Aluminum, and that is number 1 on here, and we need both of those for aluminum and silicon. So let's just say SiAl, SiAl. And the only reason I didn't refine that as ratios in the first refinement is because the electron density between silicon and aluminum is 1, which is so small that it doesn't even matter how you model it. So they're just too similar to actually model and refine to give any difference. But here, since we know the values, we can just enter them. And this one, in this case, is out of 1 because there's no mirror plane or whatever that's residing across this atom. It'll just be whatever the fraction is. So if we open up this, we see that it's SI is 1.8 atoms per formula unit out of 2, because the tetrahedral site has 2 atoms in the formula. So 1.8, what was it? 1.82 1.82 divided by 2 equals that. So this would be 0.91. 0.91. And aluminum, I will just fill the rest of the side up with the remainder there, which is 0.909, I mean. And then, but that doesn't account for all the aluminum, actually. So in here, 0.09 is, so 18 fills up the rest of it, which leaves 0.1 APFU. I think that's how the calculation works. Yes. So we have to put the rest of the aluminum in the M1 site, because aluminum also coordinates octahedrally. It's probably not going to be in the calcium site because aluminum bond lengths are much shorter. It's not going to be too happy there. So we would have to split, and I'd actually have to start naming these different things. So it's getting a little complicated. ALT for tetrahedral. And we don't need minus signs anymore because we're forcing them to be in the site and calculating out their proper ratios. AL, should I say octahedral? No, let's say 1. So we'll use the coordinates and EADP of the other octahedral thing and rename it that. 1, 1, 1. So now you can see that we're really not refining anything. We're using very few parameters to refine, which is good in a lot of ways if you can get away with it. And it's actually the proper way of doing a complete study on a crystal structure, even though it's also acceptable to refine these percentages, as long as there's, I mean, once you get over 3 occupants in the same site, then it's just kind of nonsense refining the ratios, but 2 is definitely fine. So AL1, I guess we'll just call it AM1. And then I will start naming all of these, assigning all the proper EXYZs and EADPs. And then this site, this split occupancy site, this you need to start making decisions about, because you can split some of the aluminum between that position too, like a small amount if you want. There are programs that optimize occupancies, like Occupy. I don't know if that's going to come up. Crystal structure. And the benefit of these is that rather than only using scattering factors, these refine based on optimal bond lengths and bond valence sums to assign the correct atoms to each site. But it takes a little bit of practice and knowledge getting used to those programs for making all of these proper ratios and calculating them out. This structure, the only real problem is this site, because the split site, even though it accounts for such a small bit of the structure, it can actually host a bunch of different elements. But I'm going to just make an assumption here and say that like chromium and titanium and all this other stuff is all just octahedral, and split it all between the octahedral site. AM flat should be 1. All right. So I took a little bit of a break there to figure out some stuff on the splitting all the positions up. So what I did was, on this little notepad document, is figure out a fair way of splitting up the ratios based on the microprobe data. Again, probably best to do the optimization method with the program Occupy, but I think this is a fair, I only use like a couple assumptions for this, is to, of course, with the M2 site being the size that it is, calcium and sodium have to go there. The rest, this is kind of an assumption, I'm filling with magnesium, even though the position may be vacant or split between a bunch of other stuff. But because magnesium is so dominant in this, I'm going to put the rest with the magnesium in M2 prime. So those two will go with Ca and Na will go to M2. M1 will just be the garbage can taking on everything else. The only inaccuracy in this is that I added 0.01 mg to the site, because otherwise this would have been 0.69 and it wouldn't have summed to 1, which M1 is supposed to be to total 1. The tetrahedral site has to total 2, and it does. So that is all good. And everything else is fine. So I'm going to try to make that happen and not mess up too much, even though I think I have to think about the M2 and M2 prime still. So M2 prime, so the total of the site needs to equal 1. So if it's magnesium, the magnesium component out of 0.5 needs to be whatever I said, 0.22, 22 times 0.5, 0.11. I guess I could have figured that out myself, but that's all right. And I forgot about the sodium, so we have to add that in. So MM2 is in that slightly different position that we already defined. This one is just going to be the rest, I guess. And that's too complicated of math for me right now. 0.07 times 0.5, 0.035. Okay. So that should equal, technically it's 0.5 is what that should equal because it's on a mirror plane or something. And I think that is good. Well, I have to change this. This is sodium. 1, 2, 3, 4. Damn. 1, 2, 3, 4, 5, 6. And we have to go E. It's going to need an EXYZ CM2 NM2. It's going to need an E80P also. E80P. We've got E80P CM2 MM2 prime already. This is going to be, these two I'm going to have to expand to, all right, well, we have to put in the other stuff first. So we've got aluminum. Aluminum, we need chromium still. V. CR. Well, we'll just label it R. I don't know. Why not? And 1, 2, 3. I hope this is all right. And then titanium, I decided to put in the octahedral site, even though it can occupy tetrahedral. So we will do that. .02. Why did I even look at this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Scattering factor 9 for TM1. I did that. So now all I have to do is get the ratios of these and list all the EXYZs and E80Ps, which I can use the same lines of those two. So this one's out of 0.5. So magnesium is going to be the first one which is going to be 0.7 times 0.5, which is 0.35. Iron 0.16 is 0.08. Aluminum 0.1 is 0.05. And chromium 0.02 is 0.01. Very little. And I think it's the same with titanium. Now, those have to sum to equal 0.5. So it does. And those do to 1 in this for this site, and those need to sum to 0.5 for this site, which is less obvious, but it looks, yeah, it's true. And yeah, I'm not using any free variables. Now I just have to say E, X, Y, Z for a bunch of stuff. AM1, RM1, TM1. Did that, but I have to rename these with T's. EXYZ of CM to NM2 and an EADP with MM2 prime. Okay, now let's save all that so I don't have to do anything if I really messed it up. And I think that's all correct, so I'm going to click refine. All right, it didn't totally explode at least. And this, again, since we're not refining any parameters, I mean, the R did go up by a bit, by 0.8%, it looks like, which isn't a huge deal, I don't think, because if you absolutely knew that this particular crystal had those constituents, this is absolutely the correct way of doing things. Because you're not having a bunch of variables that are just numerically optimizing what the result, what you want the result to be, which is an R of 0. But this is like a real life thing where we know what the constituents are. Maybe some of my decisions about the sites were a little bit off, but this is how you'd actually use chemical data and refine a bunch of stuff. And if you did this, you may find something else out about the structure that you didn't know. You can see that weird pi bond artifact is still there, but maybe you can find something else because you have fixed things that you know about the structure now, and you can refine atomic positions and have an overall more correct thing here. And we can output this with an acta command, and all we have to do is click refine. There's probably some stuff I'm forgetting still, or other things that I could have done, but if we do that, we can open up Vesta and try to find our structure, because it just now wrote our CIF file, and there it is. And you can see that it's split between a bunch of different stuff. Everything is split. This wasn't the best collection in the world. If I chosen a better crystal and stuff, we could have gotten a lot better. But this is how you do chemical data. Use chemical data in your refinements on ShellX.